international team of scientists, spearheaded by researchers from Newcastle University, has employed the James Webb Space Telescope to uncover a concealed veil of dust in a galaxy 70 million light-years away. This pivotal discovery highlights the supermassive black hole at the galaxy's core, known as ESO 428 G14. In this video, we will delve into how Webb's infrared abilities are exposing the secrets of cosmic dust that were once obscured. So, without further ado, let's dive in. Supermassive black holes at the centers of large galaxies, like the Milky Way, are among the most powerful and massive entities in the universe. These cosmic behemoths, ranging from millions to billions of times the mass of our Sun, fuel some of the brightest and most energetic phenomena known to science. When these black holes actively consume surrounding material, they transform into what are called active galactic nuclei, AGN, radiating immense amounts of energy across various wavelengths. However, much of the activity in AGN remains obscured by thick clouds of gas and dust that encase them, making observation challenging. This is where the James Webb Space Telescope shines. Crafted to observe the universe in infrared light, Webb can penetrate these dense clouds and uncover details that other telescopes might overlook. One of its initial targets was the galaxy ESO 428 G14, located approximately 70 million light-years away. Known as a Seyfert galaxy due to its luminous core, ESO 428 G14 has been extensively examined by telescopes like ALMA and Hubble. However, Webb's superior infrared sensitivity has enabled astronomers to explore it with unparalleled detail. The results from Webb, published in the monthly notices of the Royal Astronomical Society, revealed a captivating structure of dust enveloping the supermassive black hole at the galaxy's core. Astronomers were surprised to find that much of this dust resides outside the usual accretion disk, the ring of material feeding the black hole. This outer dust, known as polar dust, is not heated by the black hole's radiation as anticipated, but rather by shock waves produced by relativistic jets, streams of particles moving at nearly light speed ejected from the black hole's poles. A PhD student at Newcastle University leads a study within the Galactic Activity, TORUS, an outflow survey, analyzing data from the James Webb Space Telescope. The research reveals that polar dust around a supermassive black hole is heated by jets rather than by the black hole's radiation, challenging existing models of energy distribution in active galactic nuclei. For decades, the unified model of AGN has suggested that the differences between Type 1 and Type 2 AGN are mainly due to the orientation of the dusty torus surrounding the supermassive black hole. Type 1 AGN are observed more face-on, showing broad emission lines and visible accretion disks, while Type 2 AGN are seen edge-on, with the torus obscuring much of the activity. The polar dust, distinct from the torus, interacts with relativistic jets that can extend hundreds of millions of light-years into space. This interaction between jets and polar dust has profound implications for our understanding of AGN and their effects on host galaxies. Traditionally, the dusty torus was believed to be central to energy transfer within an AGN, but Webb's observations suggest that jets might play a more critical role than previously thought. The varying temperatures of the polar dust compared to the accretion disk as dust imply that the processes in these regions are more complex and diverse than the unified model predicts. The detection of extended mid-infrared emissions from the polar dust, extending up to 650 light-years from the AGN, highlights the vast scale of these interactions. The alignment of the dust with the radio jet and its perpendicular orientation to the molecular gas feeding the AGN indicate that multiple processes are occurring concurrently. This complexity suggests that the distinction between Type 1 and Type 2 AGN may need to be reassessed, with a greater focus on the roles of jets and polar dust in AGN dynamics. These findings extend beyond the ESO galaxy, prompting a re-evaluation of other AGN and raising new questions about the mechanisms driving energy transfer in these environments. If jets are indeed crucial in heating and shaping surrounding material, it could significantly alter our understanding of galaxy growth and evolution over cosmic time. Among Webb's most astounding discoveries are the oldest and most distant black holes ever observed, nestled within galaxies like GN, Z11 and Sierras 1019. These findings offer glimpses into the cosmic dawn, just hundreds of millions of years after the Big Bang. For instance, GN Z11 is a galaxy from when the universe was only about 400 million years old. At its center is a black hole approximately 6 million times the mass of our Sun, a revelation that has prompted scientists to reconsider how such massive objects could have formed so quickly after the universe's inception. This black hole's existence implies that the seeds of supermassive black holes must have emerged and evolved at an extraordinary rate, challenging and redefining previous models of black hole formation and cosmic evolution. Meanwhile, Sierras 1019 has unveiled the most distant active supermassive black hole discovered to date. This black hole, existing just over 570 million years after the Big Bang, is notable not only for its distance, but also for its relatively modest size compared to other black holes from the same era. The presence of a smaller supermassive black hole during this time raises intriguing questions about the variety of black hole formation processes in the early universe. It suggests that black holes could have formed in diverse environments and at varying rates, offering a more nuanced view of their evolution and challenging the notion that all early supermassive black holes followed a uniform growth pattern. Looking ahead, Webb's potential for future discoveries is boundless. Each new finding is expected to refine existing models and spark fresh scientific inquiries. The ongoing influence of Webb on astrophysics is profound, as it delivers the data needed to challenge old theories, validate new ones, and inspire the next generation of astronomical research. Thank you for joining me on this stellar journey. If you enjoyed this exploration into the cosmos, be sure to subscribe, like, and hit the notification bell to stay updated on the latest discoveries and insights. Until next time, keep gazing upward and asking more questions.